Hello, students. Steve Johnson here. Welcome to the class. We are now going to talk about Chapter 1 and the chemical world. I'm hoping that you guys are hearing me perfectly fine, that the microphone is clear, and that we're able to express what we're about to do. So the definition of chemistry can be the science that seeks to understand how matter behaves by studying what atoms and molecules do. And virtually everything around you is composed of a chemical. For example, you look at your toothpaste, your mouthwash, your phone, the actual device you're watching this on right now, all of it's composed of chemicals. And so we have to understand what those chemicals are made of and understand what their intrinsic basis is of how they actually exist. So all atoms are divvied up into things called atoms. Atoms are composed of all matter is composed of tiny particles called atoms. Atoms are infinitesimally small. They're smaller than your eyes, and so they're extremely small. Atoms are so small that a single grain of sand contains more atoms than there are grains of sand on a large beach. So the way that atoms come together will make different things. For example, water is just your simple H2O, right? Water, there we go. Water is just straight up H2O. And we already know what the characteristics of water is. Water is a clear liquid at room temperature. Water is wet. Water's got a boiling point of 100 degrees Celsius. Water's got a freezing point of 0 degrees Celsius. Water is the basis of life, and we are made up of 70% water. So water is a very valuable resource to us. It's a very valuable resource to our world. So that's what water is. It's got three different atoms inside of it, and that's kind of what a water molecule looks like. But if we were to compare this to, let's say, carbon dioxide. Carbon dioxide would be a carbon double bonded to an oxygen, double bonded to an oxygen. So that's a carbon dioxide molecule, but they both have three different atoms and they have different properties. And so we're going to try to understand why it is that some molecules are going to have water-like properties and why some molecules are going to have carbon dioxide-like properties. So chemistry is everything that's around us. And one thing about chemistry that's a misnomer is that chemistry is bad, chemistry is stinky, chemistry is nasty, chemistry is some of the worst stuff ever. And that's not really the case because we are made up of chemicals. And so we're not bad people, are we? Of course we're not. Everything that is a chemical is not bad. So yes, paint thinner is bad. Yes, sludge that goes into a dirty brook, yes, that's going to be poisonous and very bad for you to basically to ingest. But chemicals like I don't know, vitamins and protein and vegetables and minerals and things like that, those are going to be good for you. Olive oil is good for destroying free radicals. Good for your blood pressure as well. So those things are good for you. So when we see some things which are good for you, they are chemicals. Some things are bad for you, which are also chemicals, and so it's not all the same thing. So chemicals can be about the air that we breathe, the water we drink, toothpaste, Tylenol, toilet paper. All of those things are chemicals. And chemistry explains the properties and behavior of chemicals by helping us understand the molecules that compose them. Now, one of the best ways to understand our world is by using something called the scientific method. The scientific method is a method by which all scientists will analyze our world so that we now have a better understanding of how it behaves. And this scientific method can be used in any area of the planet, and you should still come to the same conclusion as to the way our world works. That's what the scientific method's strength is. And if the scientific method were based off of a person's opinion or their bias in terms of getting a result, then it's not going to be a very accurate method of determining what our world does. So the best way for us to understand the way the world works is by using, um, I guess, a very untinged viewpoint of the way that the world works. So the way that we're going to use this method is by first taking observations. The observations must be a measurement of or observing some aspect of nature that's happening. Today is hot. Tomorrow is cold. Um, let's see. Today it's raining. Tomorrow it's sunny. Those are going to be every day. It's going to be another observation as to what the weather's doing. So if you string apart a whole bunch of days with very similar weather patterns, like in Los Angeles, it tends to be very sunny in Los Angeles. Los Angeles is a very sunny place. So if you're in a sunny place like Los Angeles, what you're now going to do is make some kind of a tentative hypothesis that the weather is always good in Southern California. But if you saw the weather yesterday, it was relatively cloudy. And if you saw the weather maybe 2 or 3 days ago, it was also cloudy because we have June gloom and we also have like July type of heat. I guess some of the June gloom right now is burning off, and so now much of the marine layer is now disappearing from outside right now. So if you were able to see those things happening, you could make a hypothesis that in the morning it's very cloudy, but then as the marine layer burns off, it becomes much sunnier and it becomes much hotter because there is no barrier between the sun and us. So the clouds are just all going away. So we can make a hypothesis as a tentative explanation as to what's happening. Then what you can do is make a scientific law, which will always be true. So a law is essentially going to be a refined hypothesis that's never false. Hypotheses become strengthened as they are tested and tested to make sure they are true. And as a hypothesis still becomes true, then it's going to become a law which can never be broken. A scientific theory, what that does is explains the basis of why something happens. So the theory is going to be a model, which gives you a good understanding as to why something occurs. And that model does not have to be precise, but as you're testing it, you can refine the model to try to get a better understanding as to why something happens all the time, so that you have a better understanding as to what happens in the future with that event. So some observations can be made with the naked eye. Other observations emerge from experiments that rely on the use of sensitive information. A good hypothesis is falsifiable, which means you can test a hypothesis, you can test a hypothesis and see how true it is. And if it's really true, if it's a hypothesis which is going to make things really true and valid for you, it's always, if it's true, then you can basically start building on the hypothesis to develop a law, because laws are never broken. For example, if you were to drive your car 200 miles, you're going to find that the gas tank, let's say we have a gas-powered engine, the gas tank is going to be reduced if you drive it 200 miles. That's a law if you have a gas-powered car that's never going to be broken. That law will always be true. Now, if you have an EV, you drive 200 miles, you can say that the battery will be drained by 200 miles of charge. That's always true. There's no way to really say they'll ever be false. So, that's a law that will never be broken. It's really just like the law of conservation of mass. That law is always going to be true. And so you can constantly recertify those events by determining that they are always going to be true. And you can do experiments to prove how accurate those hypotheses are. And if you find that a hypothesis is falsifiable in some manner, you can then go ahead and refine the hypothesis in order to understand why something's happening or not. So the key thing to understand about the scientific method is that there must always be some kind of experimentation which is proving whether or not something is true. And if you are proving that something is always true or something is always false, then you can go ahead and reformulate your hypothesis to be truer and have a better explanation as to why things happen in our natural world. So here's a French chemist by the name of Antoine Lavoisier. Antoine Lavoisier was a chemist who was using the scientific method to understand the physical world. So what Antoine Lavoisier did was he burned a lot of wood in a metal container. He measured the wood, the weight of the wood before burning it, and then after burning it. And he allowed the gases to stay in the container. And what he found was that the mass did not change, but the actual wood itself had changed its composition. So what he was able to discover was the law of conservation of mass, is that matter is neither created nor destroyed, it's only changed in form. So here's a picture of Antoine Lavoisier. And I think that's what his wife, Mademoiselle Lavoisier, I don't remember what her name is, but let me show you something that's on here. And I'm going to go right here to, oof. Where we go? What? Oh, I took a trip to New York City and I took my children to New York City one day and we went to the Met and we actually saw his painting. That very same painting was actually in, here it is over here. Oh, stop moving. It is here somewhere. I know it is because I just saw it. So this painting is actually in the Met, and it says right here, Louis David is, I think, the artist that painted the painting. It's a portrait of Mr. and Mrs. Lavoisier in 1788. That's the painting. So that's what, that's his wife, and that's also Mr. Lavoisier. So he is the scientist who's in that painting. And this is actually hanging in the Met right now. That's where it is. It's in the Metropolitan Museum of Art in New York City. So if you were able to see that picture, come on. So there's the picture. Same picture. So Lavoisier burned substances in closed containers. He measured the mass of each container and its contents before and after burning the substance. And then he noted that there was no change in the mass during combustion. Therefore, he looked at the container and he saw there was nothing but ash inside the metal container. And he discovered that you just basically are rearranging atoms. You're not making anything, you're not losing anything, you're just rearranging atoms to make something new. But the mass is the same both before and after you burn the material. So that's why he came up with the law of conservation of mass, which states that in a chemical reaction, matter is neither created nor destroyed. And the law is not only synthesized his past observations, but it predicted future ones as well. And that's the reason why if I go to the Arco station and I fill up my gas tank, I know that I can predict that if I drive 200 miles, the gas will be gone because it's happened so many times before that there's no way for me to drive 200 miles and not go into my gas tank. So the energy in the gas tank must be used up in order for the car to go that far. So looking at atomic theory, the idea that all matter is made up of atoms is a theory with 200 years of experimental evidence to support it. But it wasn't until the 1980s that we were able to observe and examine what was happening with atoms. So we could use a mathematical model to try to represent what an atom is by using an electron tunneling microscope. And we're putting dots on a screen on a film of a copper surface in order to determine that those copper surfaces are going to light up. Those 12 cobalt atoms arranged in a circle on a copper surface. That's because of mathematical calculations which are then approximating that those atoms are existing on that copper surface. So that's how intricate the measurement is in detecting an atom. So let's do a couple of these. Classify each statement as an observation, a law, or a theory. When a metal, it says, when a metal is burned in a closed container, the mass of the container and its contents does not change. So that's going to be the law of conservation of mass. That should be a law. It doesn't say when this metal, because if it said this metal, it'd be an observation. But if it's saying when a metal, like any metal, that would be a law. That can never be broken. Matter is made up of atoms. Is that true? Yeah, that's true. That would be a law. Matter is conserved in chemical reactions. That would also be a law. So when wood is burned in a closed container, its mass does not change. That's the same thing as A. So many of these appear to be laws. Now, they appear to be laws, and one thing I don't like about these questions is that sometimes it's not clear as to what the number of measurements that are being used to make that statement. If it's one measurement, it's an observation. But if it's several of them, it's a hypothesis. And if it's always irrefutable, it's a law. And that's the best way you should be answering these types of questions. So sometimes the questions can be a little bit esoteric in order to answer them. And look for how many measurements were taken. That differentiates an observation from a hypothesis from a law. In a law, you can take as many measurements as you want to, it'll always be the same. A hypothesis will be a tentative explanation, which means it's like a preemie law. That's a hypothesis. And observations will just be one thing that happens in space. And so sometimes the language can be a little bit ambiguous. That's probably the best way of looking at it. Okay, so scientists, let's say, analyzing and interpreting data. Scientists take measurements as part of their observations. Such sets of measurements are known as scientific data, and the table below contains a set of data. Scientists must learn to analyze and interpret such data. Do you notice any patterns that are in the data? So it appears that in sample A, when you have 2.2 grams of hydrogen formed, the mass water of sample is 20 grams. So if you multiply that by 2.5, it appears that you would have the same mass of hydrogen to mass of oxygen formed. So it appears that the ratio of the mass of hydrogen to the mass of oxygen is a constant. And therefore, you know what the ratio is in terms of hydrogen and oxygen. So it should be a 2-to-1 ratio in terms of something called a mole, which we have not discussed yet. But you can see a pattern in the data which can help you to get some kind of an answer in a problem. They can also be visualized using graphs or images. Scientists must learn to understand and interpret the data contained in such graphs. When you look at a graph such as the one below, you should first examine the x's and y's and make sure you understand what each axis represents. So if you're looking at this, it's the year on the x-axis, it's the carbon dioxide concentration in parts per million on the y-axis. So wherever those two things meet on a line, you can then determine the relationship between a year and the amount of carbon dioxide concentration in parts per million. So let's look at this graph and see how to analyze this data. What was the carbon concentration? What was the concentration of carbon dioxide in 1970? So in 1970, it's about 325 parts per million. And what was it in 2020? In 2020 was much higher at 415. parts per million. So we have doubled the amount of carbon dioxide in the atmosphere. So chemistry requires calculations, and so we're going to have lots of calculations that occur when we are doing our chemistry work. So quantification means you're taking a calculator and you're getting an answer. That's what quantification is. It involves measurement as a part of observation. It is one of the most important tools in science. So two samples of water may feel equally hot to your hand, but when you measure their temperatures, you may find that one is 40 degrees Celsius, the other one is 44 degrees Celsius. And that might be helpful in terms of getting an answer. Okay, that's chapter 1. So please do your assignments in chapter 1 on mastering chemistry, and I will talk to you all soon. Thank you. Bye.